That was one of those special cases, but we definitely need to look into special cases. All right, we've got, it looks like, 4 things going on here. So we're going to be graphing 4 different things. First one, we have the x plus 2y is greater than or equal to 3. Let's get y by itself. So 2y is greater than negative x plus 3, and y is greater than negative 1/2 x plus 3/2. Okay, there's 1. Let's go with line number 2. It says 5x minus 4y is less than or equal to 16. So negative 4y is less than or equal to negative 5x plus 16. Dividing everything through by negative 4. So we're going to make sure we take 2 seconds to reverse that inequality sign. And that'll be a positive 5/4 x minus 4 when I divide by negative 4. Okay. And last but not least, we got these 2 others. And we're going to wait and kind of analyze those when we get to the graph. So let's start forming our graph here. Okay, 1, 2, 3, 4, 5. Okay. This first line, right here in blue, we have a y-intercept at 1.5, and we have a negative slope, just like we did in example 6. We're going to go down and to the right, so that way I can make sure my line is definitely decreasing as I go throughout this. It's y is greater than, so we have solid lines. Or greater than or equal to. And it's going to roughly look like that. Okay, we're going to come back and shade in just a second. Let's start out here with our next line. On the next one, make it a little bit lower, we have a y-intercept here at negative 4, and then we have a positive slope, so now we're going to be increasing. We're going to go up 5, 1, 2, 3, 4, 5, and right 4. Again, it's y is greater than or equal to, so we have a solid line. And there we go. Alright, so how are we going to handle this next one, this third one here? This third one is saying that I need all those y values that are larger than 0 but less than 2. Okay, well all the here's a y value of 0. Here's a y value of 2. So if I ask you to graph, let's do this part. If I ask you to graph y is less than or equal to 2, remember that's just a horizontal line. And I guess I should make it solid because it says less than or equal to. But that's just a horizontal line sitting right in there. And if I ask graph y equals 0, it's just a horizontal line just sitting right there on the x-axis. So what we're doing is we're talking about confining things in between these 2 horizontal lines. And then that last one, that third one, what that one's all about is a vertical line because it's x equals. Remember, anytime you get something that's x equals, it's a vertical line. And x equals 0 is just a vertical line right there on that y-axis. So it's just sitting right there. Alright, that was a crazy mess, but let's go through and now incorporate all this shading because our goal is to figure out where's all this overlapping. Where's all this solution region overlapping? With that blue line, I wanted all the y values that are larger or greater than that blue line. So we're looking at, I'm going to try to draw this small because I'm not going to go crazy with my shading, but that right there is all those y values larger or above that line. If we go to the purple one says, I also want all those y values larger than that line. So from here, I want to make sure I'm going above that line. I want to go to the larger y values, which are sitting right up there. Okay, if I stopped right there, can y'all see where the overlapping is so far? It's right in this kind of region right in here, where I've got everything where the blue and the purple both overlap. So that would be it if I just stopped right there, but we've got a couple more going on. Let's go over to this between the 2. If I wanted to shade everything, all those y values that are smaller than 2, but larger than 0, it'd be right in there, that little tube right in there. And last but not least, to get the gold going on in here, we want all the positive x values. Well, all the positive x values are obviously in quadrant 1, or everything to the right of that. Okay, so if you can kind of see, I'm going to get another color in here. Let's get just black so we can black this out. Where I see an overlapping of blue, red, purple, and yellow, it looks like it's going to be everything in this little region right here. So it's a kind of a funky shape, but it's just right in here. And if you want to go through and just make it darker, it's a good thought. So it's really obvious. So the answer to this is really that solution region right here. It's everything that's in black, and there is the solution region. So when you want to answer this on the test, all you have to do is just make it obvious. Where does all that shading overlap? And it'll be obvious. That's what they're talking about. Okay? So let's try this again. Let's go to another example. And what we're going to be doing in the next examples are we're taking the ideas of graphing these inequalities. We're going to get a lot more practice on them here in just a second, but we're going to be graphing several inequalities, and we want to see where all their overlap, where their shaded regions overlap. The only difference between what we were doing just a second ago and what we're going to be starting here in 6.2 and 6.3 is that you have to form your inequalities first. You're going to be reading some information, so reading a word problem. You're going to want to build the inequalities, the actual like equations, and then you're going to graph them and figure out where the shading overlaps. And that's what we're doing here in 6.2 and 6.3. And what we do is we call these linear programming problems. You know, every time I see the word linear programming, I think programming, oh, this has got to be computer-based. It sounds so weird, but no, it's not really computer-based at all. It's like what I have written here. It's using a system of inequalities to find your answer. We know how to graph a system of equations, or how to find a system of equations, the solution. So we either use the substitution, the elimination, or we use matrices to help solve. Well, how you solve a system of inequalities is you graph. And then you just look to see, okay, where's all that shading overlaps, okay? And that's what we're going to be doing right here. And in general, these problems are always going to ask you to maximize and minimize. And whatever the problem asks you to maximize or minimize is going to be an actual equation. Okay, so when we do these problems, you're going to get one equation and a bunch of inequalities. Everything else is going to be inequality. So you're going to have one equation, like y equals 3x plus 4. Everything else is going to be in the form of an inequality, like 2x plus y is greater than 3. Okay? That's something to keep in mind. Whatever they ask you to maximize or minimize is what you're going to be putting the equation for. So let's start here in this example 1 for this group, and we're going to read. If you'll pause the video, go to page 334, and let's pull this out and see what we can get with this problem, okay? And our goal with this problem here in example 1, or number 2 in the book, is all we're trying to do is just start the problem out basic. We want to set up the system. We're not going to carry it all the way through and graph it and find the answers. We're going to do that in later examples. Well, all we want to do here is just be able to read all this information and form the equations and the inequalities, and then we're going to stop just right there. Just do baby steps first. Okay, so in this example, we're looking at manufacturing production scheduling. We have a national business machines manufactures 2 models. And it looks like if we go to the very last sentence, it says how many units of each model should National make each month in order to maximize its monthly profit. Okay, so first of all, like we always did with our other problems, we want to figure out what our variables are going to represent. And it says how many units of each model. Well, there it go. So X is going to be the number of units of, let's say, model A, and then let's say Y is going to be the number of units of model B. And our whole goal here is we want to maximize, it says, in order to maximize profit. This right here is going to be our equation. Everything else they give us, all that other information that's given to us, is going to actually form an inequality. Okay, so let's read this through. We have 2 fax machines, A and B. Each model A costs $100 to make, and each model B costs $150. So we have a cost for A and a cost for B. And then it says the profits are $30 and $40 for each A and B. If the total number of fax machines demanded per month does not exceed 250, or 22,500. Ooh, let's stop right there for just 1 second. We got some information. The total number of fax machines produced can't be larger than 2,500. So if I have X being the number of model A's and Y being the number of model B's, then the sum of them together, X plus Y, instead of being equal, it just says we can't exceed. So it's got to be less than or equal to 2,500. There's our first inequality right there. And then going from that point, it says the company has earmarked no more than $600,000 for costs. Okay, well, if we looked back prior to this, didn't we have something and talked about costs? We know that each Model A costs 100 to make, and each Model B costs 150. So a cost, and we have a total cost. We have another inequality we can make. So if it's $100 per Model A, so times X, and $150 per Model B, that needs to be, because they have at most they can spend is $600,000. So we have to fall, we can equal it, but we have to fall for sure at least below $600,000. Okay, there's our second inequality. Now let's go to the last part. It says we want to maximize our profits. Well, there's some information that was given to us. We know the profits earned on Model A is $40 per model, or $30 for Model A and $40 for Model B. Here's my equation. I'm going to go P equals, P stands for profit, so my profit equation is going to equal $30 off of every Model A and $40 off of every Model B, and just like that. And the reason why I'm writing this as an equal sign is mainly because it says whatever you're asked to maximize or minimize is what's going to have the equal to. Okay, so normally we're like, that covered all the information there, didn't it? We would call this problem finished, but we've got to think here. This is all a word problem, isn't it? If X is supposed to represent the number of Model A and Y is going to be the number of Model B fax machines, can you ever make a negative number of fax machines? Of course not. So we're going to put this last little stipulation in here. We're going to say, well, X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. So the number of fax machines of either model obviously has to be positive. And what this is going to do is when I go to graph and do all my shading, it's going to keep it in quadrant 1.